The key to a species' survival, Darwin claimed, is its ability to adapt. And spiders are miracles of adaptation. They live everywhere around us. So far, 42,000 species of spider have been identified. Look carefully. There they are, in our homes, in our gardens. They've conquered the majority of environments. We find them high up in the mountains or on faraway islands, but you don't need to go so far. No matter where you are, there's always a spider nearby. Spiders have conquered nearly the entire Earth. They adapt, change, multiply. Only a handful of arachnologists in the world are capable of identifying new spider species. Dr. Christine Roulard is one of them. She is in charge of the extraordinary collection at the Natural History Museum in Paris, to which she keeps adding. For her, there are still tens of thousands of different spiders to discover.
In a field like this, there's an annual density of about 200 spiders per square meter, which is huge. But most of them are too small to see. So we use a variety of techniques to find them. There are many undiscovered species. We find new ones every day. And with each new species, there's a new lifestyle to observe, which deepens our understanding of spiders.
200 spiders per square meter, maybe a dozen in this clump of grass alone. To see them, you need to shift scales and enter a world where a grasshopper looks as big as an elephant, because most of them are just a few millimeters in size. So how did they colonize the planet down to the smallest little blade of grass? How did they get here?
When they're young, they're carried away on air currents. They use aerial dispersal. They're part of the aerial plankton. Spiderlings release a tiny thread from their hind end, lift their legs, and soar off on the slightest breeze. That's how spiders disperse. And they're everywhere, on every continent except at the two poles.
Depending on fate, spiders can be carried away by the wind on a great journey that can span thousands of kilometers. Some have even been captured at more than 4,000 meters altitude by testing balloons, equipped to take air samples. Sometimes, at the other end of the journey, there is a new land for spiders to colonize. Christine Roulard is on the lookout for these accidental travelers.
In trees, spiders might settle on trunks, under bark, between branches, in leaves, even quite high up in the canopy. When conducting a spider inventory, you really have to look everywhere. In fact, if spiders have survived so well over time, it's due to their ability to adapt, as well as a certain gift of evolution: silk.
Silk, this sturdy tool, produced in real time, lets spiders build a cocoon, wrap up prey, or spin a web. In his rooftop lab at the University of Oxford, Chris Holland is attempting to unwrap the secrets of this fabulous material. He studies Nephila, a species of tropical spider known to make massive webs. It's also a voracious subject.
The spiders that you see here aren't vegetarian. They eat flies, which is their favorite food. And this is how we feed them. spider silk is an amazing material. It's managing to create a web that not only holds the weight of the spider, but also absorbs all the energy from the impact of a high-speed insect. And this is using fibres that are 30 times thinner than a human hair, creating not only something that's amazing for the spider, but also for man, so a material that outperforms any of our synthetic polymers.
In order to study this material, Chris Holland harmlessly immobilizes the spiders and reels silk from them up to 30 meters at a time.
The brilliant thing about spiders is that, quite unlike a lot of animals that have to find their construction materials for their nests or their homes from the environment, for example birds finding sticks to build a nest, yet the spider managed to keep a lot of its construction materials inside its body, and inside this spider you'll see that there's enough to build 3 full webs.
Unspun silk is stored in the spider as a sort of protein soup floating in chaos. But as this soup is pulled through a specially shaped gland in the body, it undergoes an almost instantaneous transformation. As it comes out of the spider's body, the silk changes state and becomes solid. Silk is made up of 2 types of proteins: long proteins, which are perfectly aligned by spinning to create strength, and other proteins randomly linked to create elasticity. Compared weight to weight, spider silk is stronger than steel and tougher than Kevlar. But how does silk change states so quickly? In order to explain this mystery, which fascinates scientists, Chris Holland prepares a mixture made from corn flour.
This is an example of a non-Newtonian material, and it's something that behaves either as a liquid or a solid, depending on how much energy you put into it. If I try and put my hand in very, very slowly, you'll see that it sinks. But however, if I try and put my hand in very, very quickly, you'll see it behaves much more like a solid and quite differently. If I take out this material, if I put energy into it very quickly, I can crumble it like a solid, but then very slowly, and it turns again into a liquid. Inside the silk gland, the unspun silk behaves very, very similar to the material that we're using here. It's starting to be sheared very, very slowly because the silk gland is so fat. But as the silk gland narrows, the energy put into the unspun silk dope gets faster and faster and faster, and it transforms from a liquid gel into a solid fibre.
The spider has several silk glands. This enables it to vary the material properties of the silk it produces, such as strength, density, or diameter, depending on its needs. Spinning a web is a highly complex and carefully choreographed operation. The first threads, stretched out in a star shape to form a core support structure, are made with the strongest silk. Then, a temporary frame is laid outward from the center of the web. At this point, the nature of the silk changes. The spider moves back in towards the center, releasing a highly sticky, elastic silk. It swallows up the temporary frame threads as it goes. This trap's lethal weapon is sticky silk. Under an electron microscope, we see a string of pearls which form upon contact with the humidity in the air. These are minuscule droplets of glue. So as not to get caught in its own web, the spider coats the tips of its legs with a kind of wax, which doesn't stick to the glue. Early morning dewdrops reveal the perfect geometry of these structures. But their shapes are not random. Thomas Hesselberg, another researcher with the Oxford Silk Group, has his subjects working in special frames carefully arranged on the shelves of his lab. He studies how spider webs stand up against the natural elements.
If it's very windy, the spider will usually not build a web at all. But in low winds, the spider will build a specifically adapted web. So that means it will build smaller webs, takes shorter time to build, but also is less likely to be destroyed by the wind.
In the university's wind tunnel, the researcher positions a spider on its web and gradually turns up the wind velocity. The circular form is an asset since it distributes forces evenly over the entire surface of the web, but only up to a point.
If the winds are so strong that the spider risks losing the silk, the spider will take down the web. And while it's taking down the web, it will recycle the proteins in the silk so that it can use them again for when it decides to build a web the next time.
The spider recycles the silk by eating its web, and in the process, also consumes any small prey that have been left by the wayside. Generally, the spider destroys and rebuilds its web once or twice each day. Spider webs come in a huge number of different sophisticated forms. There are many different structures, which are marvels of engineering. It's thanks to this that spiders have managed to colonize all sorts of environments, including our homes. Christine Rollard doesn't merely find her research subjects in the great outdoors. Basements and attics are prime spots too. Rarely visited places where dust gathers on the webs, giving them a sinister, foreboding look. This is also the realm of a spider that can grow as big as a hand, crystallizing all our fears and anxieties.
Many people think that all spiders make geometric webs. Not so. This is an example of a sheet web with a funnel. Tegenaria make these. These spiders are commonly found in homes.
With their morphology and hairy bodies, Tegenaria, or house spiders, have a bad reputation. They're the ones we wrongly accuse of biting us in the night. House spiders are actually harmless to mankind, and yet, the legend survives. Another species commonly found in our homes is the cellar spider. It builds a loose, irregular, tangled web that traps prey as they walk by. What's special about cellar spiders is that they can spin very fast, so their predators cannot determine their shape or their position. And in some ways, this makes them invisible.
Here's another interesting web of a spider that's commonly found in homes. It's the window spider. One section of its geometric web doesn't have spirals. The spider waits in a nearby hideout that is linked to the center of the web by a signaling thread. When prey gets caught in the web, the spider reacts like a fisherman who's just had a bite on his line and races to the center of the web.
One of the most astonishing webs in the spider world has found its place in our garden hedges. But in order to see it, first you need to find it. It's no bigger than half a grain of rice.
Ah, la voilà.
Here we go. This spider has a distinctive trap. It builds a triangular web, and the spider forms a bridge between the branch of the hedge and a tension thread that holds up the triangle. When a prey flies into the web, the spider releases the tension thread, and the prey gets tangled up in the silk.
The web is what symbolizes the spider. Yet most species don't build them. Some opt for straightforward hunting. There is even a spider that secretes a silk thread with a ball of glue on the end. It then emits a chemical substance which attracts its prey. Then it captures them with a silk lasso. But you've seen nothing yet. Spiders also hunt each other. They're cannibals. Their prey is venomous and therefore dangerous to approach. One spider hunts from a distance, the spitting spider. It doesn't build a web, but throws one on its prey. Robert Suter, a professor at Vassar College near New York, is fascinated with the species and its remarkable hunting technique.
Well, the trick is going to be to get this spider down right in front of the spitting spider. Like that. Ah, there. Now, you wouldn't see anything because it happens so fast, it throws its net out in 35 milliseconds.
Impossible to see such a fleeting movement with the naked eye. To witness it, Robert Suter has developed a unique system that lets him film at very high speeds. The spitting spider is immobilized on a glass slide and lit with a powerful beam of light.
To be able to get a good view of the spit coming out at a very high speed, we need to shoot at about 2,000 frames per second.
Evolution has transformed the spider's fangs into a silk-shooting cannon that moves back and forth at speeds never before witnessed in a living creature.
This shows the fangs of a spitting spider going back and forth at about 1,000 times a second. That kind of motion can't be caused by muscles, at least not directly. because muscles can't contract that fast. But they could be caused by the fluid flowing out very fast, causing these fangs to go back and forth, which is exactly what happens when you have a hose, turn the water on, and if you're not holding the end of the hose, it whips back and forth.
The body of this spider has been seriously modified to make this hunting technique possible. It's the only species to possess an additional silk gland. This voluminous gland, located in the head, gives it a bulbous appearance. Using another type of system, Robert Suter has discovered that the spitting spider's silk has another, even more amazing quality.
In this experiment, we're going to get the spider to spit at 2 wires. When the wires get wrapped up, we'll see whether the silk has a novel property, which would be to contract. And that pulls the 2 wires together. That has the effect on a prey item that the spider spits on it and the silk contracts and the prey item then can't move. It's a good system.
With its silk net cast at 100 kilometers an hour, the spitting spider is an amazing nocturnal hunter. But the likelihood of running into one is slim. During the day, it hides beneath rocks, safely out of reach from its predators. For some species, remaining hidden for as long as possible can be a highly effective hunting technique. With ambush hunting, it's not a question of webs, but of patience. In the south of France, Christine Rollard is searching for trapdoor spiders, masters of camouflage.
Many people think trapdoor spiders are found only in the tropics, but in fact, they live in warmer regions all over the world, maybe even in your own backyard. But they're inconspicuous and very well camouflaged in their surroundings. This is the entrance of a trapdoor spider's burrow. It's closed by a silk lid covered with a variety of plant matter. When hunting, the spider props the lid slightly open, then waits just behind it for prey to walk past within its reach.
These underground hiding places have a more complicated structure than it first appears. These spiders are capable of digging a perfectly circular hole, more than 20 centimeters deep. When the temperature gets too high, the tarantula, or trapdoor spider, fashions a second trapdoor, which isolates it from the heat and from its predators. When it is not out hunting, the trapdoor spider spends the majority of its time behind this silk door. In Asia, other species of spider have improved on this hunting technique. They weave silk trip ropes. These threads are linked up to the spider's leg. All it has to do is wait until a prey makes the rope move. Closer to home, there are other ambush hunting champions, crab spiders, who inhabit the flowers in our gardens. Some of these spiders can even change color to match the flowers in a few hours' time. They then wait motionless until a prey happens within reach. Things get complicated on a flower because sometimes the prey is bigger than the predator. But the spider has a powerful weapon that plays a key role in its success: venom. The crab spider inoculates the butterfly with a neurotoxin that paralyzes it within seconds. The venom is injected through its fangs, a pair of hook-like appendages around the spider's mouth. It's generally harmless to humans, but lethal for many insects. In fact, it sets in motion an amazing process: exodigestion. When the venom penetrates the prey's body together with saliva, it liquefies the body tissue, allowing the spider to suck up its food without having to chew. Yet another spider specialty that contributes to the species' success. And the most amazing of them don't only attack insects. The Argyroneta, or diving bell spider, that lives in our swamps is the only entirely aquatic species of spider. Evolution hasn't gone so far as to give it gills. Instead, it seeks out little air bubbles from the surface that it traps and holds, thanks to the tightly packed hair on its abdomen. It builds a self-contained diving bell. What's even more amazing is the spider weaves an underwater web that it then fills with air. It's not for hunting, but for making a diving bell. The spider's venom is effective enough that it can hunt fish. Once it's got its prey, it brings it back to the bell, where the venom can take effect without getting diluted in the water. Although the Argyroneta is the only one of its kind, our fields are home to one of the largest families of spiders, with over 5,000 species, jumping spiders. With their excessively large eyes, it's easy to guess their specialty: stock hunting. They possess the most sophisticated eyes in the spider world.
Great, I'll check these tubes over here. Okay, I'll do this side. I'll let you know.
Elizabeth Jacob from the University of Massachusetts tries to understand the properties of such developed sight. With her assistant, she has created an experiment to check if jumping spiders are capable of distinguishing colors. They've placed colored sticks in a meadow fitted with a small nesting place at the top. She checks that the spiders have settled in and built a nest.
Okay, now we're going to take the spider out of its nest and put it next to a stick it's never seen before. Now we're going to test the spider with a new stick. She's moving up to the top of the vial. And she's looking around. And it's moving towards the stick.
The spider is now faced with a new stick, so it can't rely on chemical traces that it would have left in order to locate its nest. This means that it must use another sense to orient itself.
It looks like the spider recognizes this color.
In her lab, Elizabeth Jacob tries to understand how a spider only a few millimeters in size can have such detailed, accurate vision.
Jumping spiders have really excellent vision. They have the best vision of any invertebrate that lives on land. And they use their vision in all kinds of ways. In particular, they use it when they're hunting. They hunt like a cat does. When they see a prey, they stalk it like a cat stalks a mouse. They'll hunch down and sneak up on it and then leap upon it.
Jumping spiders don't just jump a few centimeters. Their highly accurate vision allows them to make incredibly acrobatic moves.
Our jumping spiders have 8 eyes. The largest eyes, the principal eyes in the front of the head, are very specialized, and they're really good at seeing spatial detail. One of the things that we're interested in my lab is how the different eyes work together. And so we use a very simple technique. We simply paint over different pairs of eyes. So what Sky's done here is painted over the principal eyes. You can see that she can see where the prey is. That's because she still has secondary eyes that are open. So she can see to her side and she can see behind her. And she actually has a pair of secondary eyes that are open in the front of her face as well. But what she can't seem to do is recognize the prey. She orients to it, but then she's backing away. So she doesn't seem to know what it is. The principal eyes have a really unusual structure. They have a fixed lens that's on the outside of the spider, and then they have a very tiny retina at the back of a long tube. And the retina is really good at seeing detail. It's got lots of cells that enable it to sense light, but it's very small. So the spider can only see a small area in front of it at any given time. But the cool thing is that this retina moves around inside the spider's eye. That whole tube inside the spider's head moves. So the spider, as it's sitting still, can look from one side to the other, much like we can.
In the case of the jumping spider, it is no longer a question of eyeballs, but eye tubes. Muscles surrounding these tubes allow them to move. Their eyes are now essential hunting tools. Night falls, but that doesn't mean hunting stops. So as not to be in competition with the fearsome jumping spiders, evolution has bestowed some species of wolf spider with night vision. When Robert Suter shines his headlamp on the grass in this field, he sees the eyes of wolf spiders gleaming in the dark, like cat's eyes.
What's happening to the spider is the light coming to it has one chance of interacting with a photoreceptor in the eye, and another chance because it bounces off a little mirror-like device inside the eye. So it has a second chance to interact with a photoreceptor.
Deer, dogs, cats all have eyes that will shine back at you. So evolution has seen fit in a way to enhance the vision of nocturnal mammals. It also enhances the vision of wolf spiders. They've come up with the same answer.
Wolf spiders and jumping spiders are the exception that proves the rule. Most spiders have poor vision.
Spiders perceive their external environments mainly through vibrations. They have sensory organs all over their legs, different types of bristles, which can detect vibrations.
Spiders don't possess an auditory system, but the hairs on their legs are ultra-sensitive receptors. so sensitive that they can pick up the slightest movement of air produced by an insect's wings. The spider's entire communication system relies on this ability to perceive sound and vibrations that are inaudible to the human ear.
Leaf litter provides a living environment for spiders, but it's also a means of sensing vibrations caused by prey. But spiders also use the vibrations to communicate with a mate.
For some species, these movements and vibrations are indispensable for courtship, signals which are even inaudible to the ears of a scientist. George Uwitz from the University of Cincinnati specializes in spider communication. He studies a particular type of wolf spider, typically found in North America. For over 20 years, he's been trying to decipher their highly elaborate body language.
On this leaf, a female spider has laid down silk with chemical cues, which will stimulate the male to use a courtship display. I'm going to use a laser vibrometer, a very sensitive recording instrument, to record those sounds on this leaf when I put the male spider on it, and he should demonstrate courtship behavior in response to the silk on the leaf.
The male uses the dry leaf like a drum in hopes that the female will detect his calls. He uses his entire body weight to make the most powerful sounds possible.
Vibratory signals can contain a lot of information about the male that the female may be able to assess. For example, the amplitude, frequency of a seismic signal through a substrate may allow the female to assess the male's size, and the duration of the signal and the pulse rate of that signal may say something about the male's vigor or health. What we find when we analyze these and examine video simultaneously, we see that the visual signals and the vibratory signals are produced simultaneously. As a consequence, these multimodal signals make for a very effective and rather dramatic display. It's very effective at attracting the attention of the female.
But how should we interpret these signals? Another researcher, Dave Clark, has discovered that the wolf spider reacts the same way to a spider on a screen as to a real one.
It's a good thing wolf spiders have such excellent vision. What we're going to do today is try and show them some varieties of males that have different sorts of stimuli which include maybe even enlarging tufts, such as in this sequence here. We could even do such things as change the behavior of the spider by making it move faster across the screen, changing the rate of its movement or other aspects of it.
The front legs of these spiders are designed for visual communication. They are covered with long hairs that act like flags. The virtual male begins a courtship display. Our male follows suit. He tries to get the upper hand in order to attract the attention of a hypothetical female. This copycat behavior is unique among invertebrates.
The role of visual displays in courtship is incredibly important. It might be used for species recognition. It could be used to attract a mate from long distances. And in the case of our wolf spiders, which have exceptionally good vision and high visual acuity, that live in these very complex leaf litter environments, it's probably used to attract female attention from long distances and to help these males distinguish themselves from the backgrounds against which they live.
If the visual signals are so important during courtship, what role do they play for the jumping spiders, whose vision is so developed? Damian Elias from the University of California has the special privilege of studying the most elaborate courtship displays in the spider kingdom. He positions a sleeping female jumping spider in the center of a small drum linked to a laser vibrometer. He then rotates the spider to face its partner.
So once the male is done, we have to position him so he sees the female.
For the male, mating is risky business. Spiders are cannibals, and males are often smaller than females. This female jumping spider will only mate once in her entire lifetime. So she needs to be sure she chooses the right partner. The male has to prove he's the best, the fittest, and with such keen vision, the slightest faux pas in this elaborate dance won't go unnoticed.
All the while these legs are being moved, the abdomen is just moving very, very rapidly because it's the abdomen that is producing these vibrations and not the legs. So this is the fast leg motions, and this is going to show that little reach behavior. And so you see when the male does this reach display, and he comes very, very rapidly, and he touches the female, and you can even see the hairs bend as he slightly caresses the female there. And then he continues to go upon these really rapid leg flicks.
Evolution has played its part for the males. Their testicles are not linked to their reproductive organ. The male deposits some drops of sperm on a little web. He then fills up his copulatory bulbs, which are smaller legs at the front of his body. Mating is a high-risk game with one simple rule: mate without being eaten. Some occupy the female with a circular dance, then tie her up discreetly with a silk thread. But it is the golden orb weaver that runs the highest risk. The difference in size between the male and the female is enormous, and the male can only reach the female when she's busy eating prey. His approach is slow and thoughtful. The most complicated task is reaching her abdomen without being eaten. All the male has to do is introduce his pedipalps. This time, the male gets away in good shape. Still, once the deed is done and the danger is past, this male can't resist the temptation of a nice meal. The golden rule among spider couples: don't overstay your welcome. At some point after mating, the female lays her eggs. Once again, evolution has come up with some sophisticated strategies. Some spiders use their weaving expertise to ensure that their young can survive a long, cold winter.
A lot of species only live for a year. For those that lay their eggs in the fall, like the banded epeira, this is a banded epeira cocoon, they protect their eggs by keeping them warm so they can make it safely through the winter, when temperatures often drop quite low. It's very sturdy, and there's a big difference between the temperature outside and the temperature inside, with all these layers of silk.
To build this high-tech nursery, the female banded epeira has developed a complex technique. First, she lays her eggs under a silk dome. Then, she wraps her hanging treasure in different layers of silk, each with a specific function. The first layer secures the eggs in place. Next, the spider produces a very light, fleecy silk. Once the eggs have hatched, this layer will provide a kind of chamber where the spiderlings can spend their first weeks protected from the cold. The cocoon is now formed, and the mother spider covers it with a stiff envelope of silk. Finally, to hide her work and protect it from predators, she covers the cocoon with a layer of brown camouflage. It took 8 hours for the banded garden spider to create this little gem. Exhausted by her work, the female spider will soon die, but her descendants has now been ensured. Not all spiders are born orphans, though. In some species, females carry the cocoon on their back until the young emerge. Like the wolf spider, which lets its young climb onto its back. The researchers have even seen females carry up to 100 little ones for over a week. Out of the massive clutch of eggs produced, only 1% of the eggs will grow to become an adult spider. On average, a spider couple leaves behind only 2 descendants, just enough to carry on the species. But before being able to take their turn to reproduce, the young adults must confront a number of predators.
The reason spiders have been so successful in conquering the world is because they've developed highly diversified strategies for dealing with all types of environments. In fact, they've relied much more on individual innovation than mass invasion.
Highly effective innovations that have made them the greatest regulators of insects, way ahead of birds. Each year, spiders alone capture more than 400 million insects per square kilometer. Their ecological role is crucial. And yet, spiders can't seem to shake their bad reputation. It's up to us to learn to look at them without fear as consummate role models whose lesson can be summed up in a single word: adapt.